Hello everyone and welcome to this interesting session on Q learning. Now let's step into the world of reinforcement learning, another beautiful branch of artificial intelligence which lets machine learn on their own in a way different from traditional machine learning. Throughout our lives, we perform a number of actions to pursue our dreams. Some of them bring us good rewards and others do not. Along the way, we keep exploring different paths and figure out which action might lead to better rewards. We work hard towards our dreams, utilizing the feedback we get based on our actions to improve our strategies. They help us determine how close we are to achieving our goals. Our mental states change continuously, representing this closeness. In that description of how we pursue our goal in daily life, we framed for ourselves a representative analogy of reinforcement learning. Now, let me summarize the above example, reformatting the main points of interest. Our reality contains environment in which we perform numerous actions. Sometimes we get good or positive rewards for some of these actions in order to achieve the goals. Now, during the entire course of life, our mental and physical states evolve. We strengthen our action in order to get as many rewards as possible. Now, the key entities of interest are the environment, the action, reward, and the state. Now, this whole paradigm of exploring the environment and learning through actions, rewards, and states establishes the foundation of reinforcement learning. So, reinforcement learning solves a particular kind of problem where decision making is sequential and the goal is long term, such as game playing, robotics, resource management, or logistics. Now, for a robot, an environment is a place where it has been put to use. Now remember, this robot is itself the agent. For example, an automobile factory where a robot is used to move materials from one place to another. Now the tasks we discussed just now have a property in common. Now these tasks involve an environment and expect the agent to learn from the environment. Now this is where traditional machine learning fails and hence the need for reinforcement learning. Now, it is good to have an established overview of the problem that is to be solved using the Q learning or the reinforcement learning. So it helps to define the main components of a reinforcement learning solution, that is the agent, environment, action, rewards, and states. So let's suppose we are to build a few autonomous robots for an automobile building factory. Now these robots will help the factory personnel by conveying them the necessary parts that they would need in order to build the car. Now these different parts are located at 9 different positions within the factory warehouse. The car part include the chassis, wheels, dashboard, the engine, and so on. And the factory workers have prioritized the location that contains the body or the chassis to be the topmost. Now they have provided the priorities for other locations as well, which we will look into the moment. Now these locations within the factory look somewhat like this. So as you can see here, we have L1, L2, L3, all of these stations. Now, one thing you might notice here that there are little obstacle present in between the locations. So L6 is the top priority location that contains the chassis for preparing the car bodies. Now the task is to enable the robots so that they can find the shortest route from any given location to another location on their own. Now the agents in this case are the robots. The environment is the automobile factory warehouse. So let's talk about the states. So the states are the location in which a particular robot is present in the particular instance of time, which will denote its states. Now machines understand numbers rather than letters, so let's map the location codes to number. So as you can see here, we have mapped location L1 to the state 0, L2 and 1, and so on. We have L8 as state 7 and L9 at state 8. Well, next, what we're going to talk about are the actions. So in our example, the action will be the direct location that a robot can go from a particular location, right? Consider a robot that is at L2 location, and the direct locations to which it can move are L5, L1, and L3. Now, the figure here may come in handy to visualize this. Now, as you might have already guessed, the set of actions here is nothing but the set of all possible states of the robot. For each location, the set of actions that a robot can take will be different. For example, the set of actions will change if the robot is in L1 rather than L2. So if the robot is in L1, it can only go to L4 and L2 directly. Now that we are done with the states and the actions, let's talk about the rewards. So the states are basically 0, 1, 2, 3, 4, and the actions are also 0, 1, 2, 3, 4 up till 8. Now the rewards now will be given to a robot if a location, which is the state, is directly reachable from a particular location. So let's take an example. Suppose L9 is directly reachable from L8, right? So if a robot goes from L8 to L9 and vice versa, it will be rewarded by 1. And if a location is not directly reachable from a particular location, we do not give any reward, a reward of 0. Now the reward is just a number here and nothing else. It enables the robots to make sense of their movements, helping them in deciding what locations are directly reachable and what are not. Now with this queue, we can construct a reward table which contains all the reward values mapping between all possible states. So as you can see here in the table, the positions which are marked green have a positive reward. And as you can see here, we have all the possible rewards that a robot can get by moving in between the different states. Now comes an interesting decision. Now remember that the factory administrator prioritized L6 to be the topmost. So how do we incorporate this fact in the above table? Now this is done by associating the topmost priority location with a very high reward than the usual ones. So let's put 999 in the cell L6, L6. Now the table of rewards with a higher reward for the topmost location looks something like this. We have now formally defined all the vital components for the solution we are aiming for the problem discussed now. We will shift gears a bit and study some of the fundamental concepts that prevail in the world of reinforcement learning and Q-learning. So first of all, we'll start with the Bellman equation. Now consider the following square of rooms, which is analogous to the actual environment from our original problem, but without the barriers. Now suppose a robot needs to go to the room marked in the green from its current position A using the specified direction. Now how can we enable the robot to do this programmatically? One idea would be introduce some kind of a footprint which the robot will be able to follow. Now here a constant value is specified in each of the rooms which will come along the robot's way if it follows the direction specified above. Now in this way, if it starts at location A, it will be able to scan through this constant value and will move accordingly. But this will only work if the direction is prefixed and the robot always starts at the location A. Now consider the robot starts at this location rather than its previous one. Now the robot now sees footprints in two different directions. It is, therefore, unable to decide which way to go in order to get the destination, which is the green room. It happens primarily because the robot does not have a way to remember the directions to proceed. So our job now is to enable the robot with a memory. Now this is where the Bellman equation comes into play. So as you can see here, the main reason of the Bellman equation is to enable the robot with a memory. That's the thing we're going to use. So the equation goes something like this. V of S gives maximum of A, R of S comma A plus gamma of V S dash, where S is a particular state, which is a room, A is the action moving between the rooms, S dash is the state to which the robot goes from S, and gamma is the discount factor. Now we'll get into it in a moment, and obviously R of S comma A is a reward function which takes a state S and action A and outputs the reward. Now V of S is the value of being in a particular state, which is the footprint. Now we consider all the possible actions and take the one that yields the maximum value. Now there is one constraint, however, regarding the value footprint, that is the room marked in the yellow just below the green room. It will always have the value of 1 to denote, that is one of the nearest room adjacent to the green room. Now this is also to ensure that a robot gets a reward when it goes from a yellow room to the green room. Let's see how to make sense of the equation which we have here. So let's assume a discount factor of 0.9. As you remember, gamma is the discount value or the discount factor, so let's take it 0.9. Now for the room which is marked just below the 1 or the yellow room, which is the asterisk mark, for this room, what will be the V of S? That is the value of being in a particular state. So for this, V of S would be something like maximum of A will take 0, which is the initial of RS comma A, plus 0.9, which is gamma, into 1. That gives us 0.9. Now here the robot will not get any reward for going to a state marked in yellow, hence the RS comma A is 0 here. Now the robot knows the value of being in the yellow room, hence V of S dash is 1. Following this, for the other states, we should get 0.9. Then again, if we put 0.9 in this equation, we get 0.81, then 0.729, and then we again reach the starting point. So this is how the table looks with some value footprints computed from the Bellman equation. Now, a couple of things to notice here is that the max function helps the robot to always choose the state that gives it the maximum value of being in that state. Now, the discount factor gamma notifies the robot about how far it is from the destination. This is typically specified by the developer of the algorithm that would be installed in the robot. Now, the other states can also be given their respective values in a similar way. So as you can see here, the boxes adjacent to the green one have 1. And if we move away from 1, we get 0.9, 0.81, 0.729, and finally we reach 0.66. Now the robot now can proceed its way through the green room, utilizing these value footprints even if it's stopped at any arbitrary room in the given location. Now if a robot lands up in the highlighted sky blue area, it will still find 2 options to choose from. But eventually, either of the paths will be good enough for the robot to take because of the way the value footprints are now laid out. Now, one thing to note here is that the Bellman equation is one of the key equations in the world of reinforcement learning and Q-learning. So if we think realistically, our surroundings do not always work in the way we expect. There is always a bit of stochasticity involved in it. Now this applies to robot as well. Sometimes it might so happen that the robot's machinery got corrupted. Sometimes the robot may come across some hindrance on its way, which may not be known to it beforehand, right? And sometimes even if the robot knows that it needs to take the right turn, it will not. So how do we introduce this stochasticity in our case? Now here comes the Markov decision process. Now consider the robot is currently in the red room and it needs to go to the green room. Now let's now consider the robot has a slight chance of dysfunctioning and might take the left or the right or the bottom turn instead of taking the upper turn in order to get to the green room from where it is now, which is the red room. Now the question is, how do we enable the robot to handle this when it is out in the given environment, right? Now, this is a situation where the decision making regarding which turn is to be taken is partly random and partly under the control of the robot. Now, partly random because we are not sure when exactly the robot might dysfunctional, and partly under the control of the robot because it is still making a decision of taking a turn right on its own and with the help of the program embedded into it. So, a Markov decision process is a discrete time stochastic control process. It provides a mathematical framework for modeling decision making in situations where the outcomes are partly random and partly under the control of the decision maker. Now we need to give this concept a mathematical shape, most likely an equation, which then can be taken further. Now you might be surprised that we can do this with the help of the Bellman equation with a few minor tweaks. So if we have a look at the original Bellman equation, v of x is equal to maximum of r s comma a plus gamma v of s dash. What needs to be changed in the above equation so that we can introduce some amount of randomness here. As long as we are not sure when the robot might not take the expected turn, we are then also not sure in which room it might end up, in which is nothing but the room it moves from its current room. At this point, according to the equation, we are not sure of the S dash, which is the next state, or the room, but we do know all the probable turns the robot might take. Now, in order to incorporate each of these probabilities into the above equation, we need to associate a probability with each of the turns to quantify the robot if it has got any X% chance of taking this turn. Now, if we do so, we get Ps is equal to maximum of Rs comma a plus gamma into summation of S dash Ps comma a comma S dash into V of S dash. Now the Ps, A and S dash is the probability of moving from room S to S dash with the action A. And the summation here is the expectation of the situation that the robot incurs, which is the randomness. Now let's take a look at this example here. So when we associate the probabilities to each of these turns, we essentially mean that there is an 80% chance that the robot will take the upper turn. Now, if we put all the required values in our equation, we get V of S is equal to maximum of R of S comma A plus gamma of 0.8 into V of room up plus 0.1 into V of room down, 0.03 into room of V of room left plus 0.03 into V of room right. Now note that the value footprints will now change due to the fact that we are incorporating stochastically here. But this time we will not calculate those value footprints. Instead, we will let the robot to figure it out. Now up until this point, we have not considered about rewarding the robot for its action of going into a particular room. We are only rewarding the robot when it gets to the destination. Now, ideally, there should be a reward for each action the robot takes to help it better assess the quality of the actions, but the rewards need not to be always be the same. But it is much better than having some amount of reward for the actions than having no rewards at all, right? And this idea is known as the living penalty. In reality, the reward system can be very complex, and particularly modeling sparse rewards is an active area of research in the domain of reinforcement learning. So by now we have got the equation which we have. So what we're going to do is now transition to Q-learning. So this equation gives us the value of going to a particular state, taking the stochasticity of the environment into account. Now, we have also learned very briefly about the idea of living penalty, which deals with associating each move of the robot with a reward. So Q-learning possesses an idea of assessing the quality of an action that is taken to move to a state rather than determining the possible value of the state which is being moved to. So earlier we had 0.8 into V of S1, 0.03 into V of S2, 0.1 into V of S3, and so on. Now, if we incorporate the idea of assessing the quality of the action for moving to a certain state, so the environment with the agent and the quality of the action will look something like this. So instead of 0.8 V of S1, we'll have Q of S1, comma A1, we'll have Q of S2, comma A2, Q of S3. Now the robot now has 4 different states to choose from. And along with that, there are 4 different actions also for the current state it is in. So how do we calculate Q of S comma A, that is the cumulative quality of the possible actions the robot might take? So let's break it down. Now from the equation V of S equals maximum of A R S comma A plus gamma summation S dash P S A S dash into V of S dash. If we discard the maximum function, we have R S of A plus gamma into summation P and V. Now, essentially in the equation that produces V of S, we are considering all possible actions and all possible states from the current state that the robot is in. And then we are taking the maximum value caused by taking a certain action, and the equation produces a value footprint which is for just one possible action. In fact, we can think of it as the quality of the action. So Q of S comma A is equal to R S comma A plus gamma of summation P and V. Now that we have got an equation to quantify the quality of a particular action, we are going to make a little adjustment in the equation. We can now say that V of S is the maximum of all the possible values of Q of S comma A, right? So let's utilize this fact and replace V of S dash as a function of Q. So Q S comma A becomes R of S comma A plus gamma of summation P S A S dash and maximum of the Q S dash A dash. So the equation of V is now turned into an equation of Q, which is the quality. But why would we do that? Now, this is done to ease our calculations because now we have only one function Q, which is also the core of the dynamic programming language. We have only one function Q to calculate, and R of S comma A is a quantified metric which produces reward of moving to a certain state. Now the qualities of the actions are called the Q values, and from now on we will refer to the value footprints as the Q values. An important piece of the puzzle is the temporal difference. Now temporal difference is the component that will help the robot calculate the Q values with respect to the changes in the environment over time. So consider our robot is currently in the mark state and it wants to move to the upper state. One thing to note that here is that the robot already knows the Q value of making the action, that is moving to the upper state. And we know that the environment is stochastic in nature, and the reward that the robot will get after moving to the upper state might be different from an earlier observation. So how do we capture this change, the real difference? We calculate the new Q S, A with the same formula and subtract the previously known Q S A from it. So this will in turn give us the new QA. Now the equation that we just derived gives the temporal difference in the Q values, which further helps to capture the random changes in the environment which may impose. Now the new Q S, A is updated as the following. So Qt of S, A is equal to Qt minus 1 S, A plus alpha TDT of A, S. Now here alpha is the learning rate which controls how quickly the robot adapts to the random changes imposed by the environment. The Qt S, A is the current state Q value, and the Qt minus 1 S, A is the previously recorded Q value. So if we replace the TD S, A with its full form equation, we should get Qt of S, A is equal to Qt minus 1 of S, A plus alpha into R of S, A plus gamma maximum of Q S dash A dash minus Qt minus 1 S, A. Now that we have all the little pieces of Q learning together, let's move forward to its implementation part. Now this is the final equation of Q learning, right? So let's see how we can implement this and obtain the best path for any robot to take. Now to implement the algorithm, we need to understand the warehouse location and how that can be mapped to different states. So let's start by recollecting the sample environment. So as you can see here, we have L1, L2, L3 till L9. And as you can see here, we have certain borders also. So first of all, let's map each of the above locations in the warehouse to numbers or the states so that it will ease our calculations, right? So what I'm going to do is create a new Python 3 file in the Jupyter notebook, and I'll name it as QLearning NumPy. Okay, so let's define the states. But before that, what we need to do is import NumPy because we're going to use NumPy for this purpose. And let's initialize the parameters, that is the gamma and alpha parameters. So gamma is 0.75, which is the discount factor, whereas alpha is 0.9, which is the learning rate. Now next what we're going to do is define the states and map it to numbers. So as I mentioned earlier, L1 is 0 and till L9 we have defined the states in the numerical form. Now the next step is to define the actions, which is, as mentioned above, represent the transition to the next state. So as you can see here, we have an array of actions from 0 to 8. Now what we're going to do is define the reward table. So as you can see here, it's the same matrix that we created just now, that I showed you just now. Now if you understood it correctly, there isn't any real barrier limitation as depicted in the image. For example, the transition L4 to L1 is allowed, but the reward will be 0 to discourage that path. Or in tough situation, what we do is add a -1 there so that it gets a negative reward. Now in the above code snippet, as you can see here, we took each of the states and put ones in the respective state that are directly reachable from the certain state. Now if we refer to that reward table once again, what we created, the above array construction will be easy to understand. But one thing to note here is that we did not consider the top priority location L6 yet. We would also need an inverse mapping from the states back to its original location, and it will be cleaner when we reach to the utter depths of the algorithms. So for that, what we're going to do is have the inverse map location. State to location, we will take the distinct state and location and convert it back. Now what we'll do is we'll now define a function getOptimal, which is the getOptimal route, which will have a start location and an end location. Don't worry, the code is big, but I'll explain you each and every bit of the code. Now the getOptimalRoute function will take two arguments, the starting location in the warehouse and the end location in the warehouse respectively. And it will return the optimal route for reaching the end location from the starting location in the form of an ordered list containing the letters. So we'll start by defining the function by initializing the q values to be all zeros. So as you can see here, we have given the q values to be 0, but before that, what we need to do is copy the reward matrix to a new one. So this is the rewards new. And next again, what we're going to do is get the ending state corresponding to the ending location. And with this information, automatically we'll set the priority of the given ending state to the highest one. Right? We are not defining it now, but we'll automatically set the priority of the given ending state as 999. So what we're going to do is initialize the q values to be 0. And in the q learning process, what you can see here, we are taking I in range 1000, and we're going to pick up a state randomly. So we're going to use the np.random rand int. And for traversing through the neighbor location in the same maze, we're going to iterate through the new reward matrix and get the actions which are greater than 0. And after that, what we're going to do is pick an action randomly from the list of the playable actions nearest to the next state. We're going to compute the temporal difference, which is TD, which is the rewards plus gamma into the queue of next state. And we'll take np.argmax of queue of next state minus queue of the current state. We're going to then update the q values using the Bellman equation. As you can see here, we have the Bellman equation, and we're going to update the q values. And after that, we're going to initialize the optimal route with the starting location. Now, here we do not know what the next location yet. So initialize it with the value of the starting location, which again is the random location. Now, we do not know about the exact number of iterations needed to reach to the final location. Hence, while loop will be a good choice for the iteration. So we're going to fetch the starting state, fetch the highest q value penetrating to the starting state. We go to the index of the next state, but we need the corresponding letter. So we're going to use that state to location function we just mentioned there. And after that, we're going to update the starting location for the next iteration. And finally, we'll return the route. So let's take the starting location of L9 and the end location of L1 and see what part do we actually get. So as you can see here, we get L9, L8, L5, L2, and L1. And if you have a look at the image here we have, if we start from L9 to L1, we got L8, L5, L2, L1, L8, L5, L2, L1. That would yield us the maximum value or the maximum reward for the robot. So now we have come to the end of this Q learning session, and I hope you got to know what exactly is Q learning with the analogy all the way starting from the number of rooms. And I hope the example which I took, the analogy which I took, was good enough for you to understand Q learning, understand the Bellman equation, how to make quick changes to the Bellman equation, and how to create the reward table, the Q table, and how to update the Q values using the Bellman equation. What does alpha do? What does gamma do? So guys, if you like this video, give it a thumbs up. And if you want to see more videos like this and be technologically updated every time, do subscribe to our channel. There are a lot of videos regarding deep learning, AI, machine learning, DevOps, all the different types of technology. We even have blockchain with us. So if you have any queries regarding this session, please feel free to mention it in the comment section below. Till then, thank you and happy learning.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!